Hello everyone, my name is Tongjin Zhang. I'm from Department of Chemistry, Tsinghua University. It's my honor to give this speech. Today, the title of my speech is Research on Excited State Processes in Novel Micro or Nanolasing Materials and Devices. First, here's my personal profile. I graduated from Qingdao University with a bachelor's degree in composite materials and engineering. After graduation, I was admitted to the Institute of Chemistry, Chinese Academy of Sciences, where I conducted research on organic, optical, electronic devices and materials. During my time here, I received several honors, including the National Scholarship and the Director's Award. After obtaining my doctoral degree, I joined Tsinghua University as a postdoctoral researcher. Next, I will present my personal research findings. With the advancement of technology, laser technology is also continuously developing. Micro and nano lasers, in particular, represent a cutting-edge research area at the intersection of laser technology and nanoscience. Since the successful development of the first zinc oxide nanowire lasers in 2001, inorganic semiconductors have played a crucial role in the research of micro and nano lasers and modular. Researchers have subsequently reported on various inorganic semiconductor-based devices, including surface plasma fluorescent lasers below the optical diffraction limit, topological lasers, or optical controlled photonic logic elements, and prototypes of photonic integrated circuits. This series of research results demonstrate the advantages of inorganic semiconductors, such as high material stability and excellent optical electronic properties. However, inorganic semiconductors have a relatively fixed gain range, making it difficult to achieve broadband wavelength tuning. Their variety is also limited, and their preparation conditions are quite strict, often requiring high temperature and high vacuum conditions. These factors largely limited the further application of inorganic materials in the field of nanophotonics. Compared to inorganic materials, novel micro and nano lasers represented by organic semiconductors, perovskites, and quantum dots possess excellent solution processability and rich excited processes. Through compositional control and size tuning, they can achieve laser emission from the visible to near infrared range, offering significant advantages in the construction of nanophotonic functional devices. Currently, micro and nano lasers are mainly resolved through pulsed laser excitation, which is crucial for studying ultra-fast excited processes in materials. However, for practical applications, developing miniaturized electrically pumped micro and nano lasers is more beneficial for photonic chip integration and other applications such as displays and sensing. Although recent studies have shown a nonlinear relationship between current density and luminescence intensity in organic semiconductor and quantum dot materials through rational material design and the incorporation of suitable cavity structures, including distributed Bragg reflector cavities and distributed feedback cavities, have claimed to achieve electrically pumped lasing. This evidence alone is insufficient to confirm laser operation. Further evidence, including temporal and spatial coherence, is required, indicating that achieving electrically pumped laser still presents significant challenges. The challenges mainly including the contradiction between large optical gain and high carrier mobility in gain materials. Generally, achieving high carrier mobility requires tightly packed molecular structures, but this tight packing can lead to fluorescence quenching. A balance between these two factors is necessary. Compared to optical pulp devices, the introduction of electrodes and transport layers in electrically pumped devices introduces additional losses, significantly increased the laser threshold. Furthermore, the presence of non-radiative process in the material greatly limits the realization of electrically pumped lasers. In organic semiconductors, electrically injected carriers generate singlets and triplets excitons in a 1:3 ratio. In most cases, triplet excitons cannot produce stimulated emission and undergo absorption to high-energy triplet states, as well as annihilation processes with singlets excitons. These processes hinder the improvement of photonic performance and electrically pumping. In addition, the imbalance of electron and hole interaction in the material generates porins, leading to additional optical loss processes. Faced with various pathways that limit the realization of electrically pumped lasers mentioned above, we start from material design and micro cavity structure to control the excited states and obtain high-performance lasers. Based on this, we combine it with electroluminescence devices to advance towards electrically pumped lasers. Following this approach, we mainly carry out the following two aspects of work. First, let me introduce the first work, thermally activated lasings in organic microcrystals toward laser displays. The unique energy level structure in similarly activated delayed fluorescence materials allows for the utilization of triplet excitons through the reversible intersystem crossing process, potentially solving the problem of triplet exciton losses in micro and nano lasers. However, experimental evidence to the feasibility of this concept is still lacking. Therefore, we select TDF systems with high luminescence efficiency and high RISC efficiency based on laser theory, and combine them with high-quality microcavities to achieve thermally activated laser emission. TDF material adopted CBP microstalls were obtained through a solution co-assembly method. Selected area in electron diffraction conditions confirm that the introduction of TDF molecules didn't significantly affect the structure of the CBP microcrystals, maintaining excellent crystallinity. Benefiting from this regular morphology, a nonlinear relationship between pump power and emission intensity and optical pumping was observed, indicating laser emission in this system. By fitting the model species in the laser spectrum at different sizes, the laser resonance mode in the microcrystals was determined to be a whispering Garried mode. A unique thermally activated lasing phenomenon was observed during variable temperature laser characterization, where the laser intensity gradually increased with the increasing temperature. This experimentally demonstrates that triplet excitons in the system can be captured and used for singlet stimulated emission, achieving high-performance laser output. Furthermore, thanks to the excellent solution processability and compressibility in other materials of the selected material, we developed a solution-confined growth method to obtain a red, green, and blue laser array. Each pixel in the array is a laser capable of laser emission. We use this laser array as a display panel, achieving pattern display through Kelvin nanometer scanning. Next, I will introduce my second project, recycling of triplets into singlets for high-performance organic lasers. The triplet upper conversion process refers to the correlation between two triplet excitons and the electrical injection. When the triplet exciton density is sufficiently high, producing a singlet exciton with twice the energy, which then radiates light. This has been proved to improve the external quantum efficiency of electroluminescent devices, thus achieving the utilization of electrically injected triple exciton. To this end, we constructed the exciton cycle system shown in the figure and built in a microcavity to advance towards electrically pumped lasers. First, regarding material selection, the large overlap between the sensitizer emission and the gain media absorption spectrum, as well as the change in sensitizer lifetime before and after doping with the gain media, confirm the existence of an efficient energy transfer process between the two, enabling the above-mentioned excited process. Similar to the singlet energy transfer process mentioned above, the corresponding triplet energy levels are obtained through the phosphorescence spectra of the gain media and the sensitizer, thus confirming that energy transfer between the triplet excitons can be achieved in the selectively sensitizer and gain media, promoting high-performance lasers. After we fabricated distributed feedback lasers using electron beam lithography and combined with a self-built micro-nanolaser characterization devices, achieved long-threshold single-mode lasers emission and optical pumping, and an external magnetic field. The decrease in laser intensity with the increasing magnetic field strength indicates that the singlet exciton generated by the triplet upcorrosion process participate in the stimulated emission process, further transition absorption characterization through a longer gain lifetime, which is conducive to the realization of continuous wave lasers and electrically pumped lasers. Furthermore, by introducing the above long-threshold gain materials into an electroluminescent device and optimizing the device structure, we obtained a maximum external quantum effect of 4.5%, exceeding the theoretic EQE limit of typical fluorescent OLED devices. This proves that triplet excitons are utilized in the electroluminescent devices, suppressing the annihilation between triplet and singlet excitons and avoiding efficiency roll-off at high current density. Furthermore, by combining the distributed feedback microcavity used in optical pump lasers with the above-mentioned electroluminescent devices, the emission spectrum is significantly narrowed due to the microcavity modulation effect. Thanks to the small area of the microcavity, the use of a pulsed power supply to further reduce dual heating during the electrical injection process The device can achieve ultra-high current density injections, thus enabling the construction of high-performance microcavity devices. Finally, in summary, my work aims at the ultimate goal of realizing electrically pumped lasers by selecting suitable optical electronic materials and combining them with experience in nanostructure fabrication and characterization. I managed and controlled various loss pathways that hinder the realization of electrically pumped lasers from two aspects: controlling the excited states and constructing new stimulated emission mechanisms. Through various spectroscope characterization methods, the excited states in the materials are clearly identified, thereby achieving high-performance laser emission and the construction of mercury-based electroluminescent device. Although the electrically pumped lasers is not achieved in my works, and there are also many challenges in the future with the cooperation with each other. I believe this can be achieved in the future. That's all. Thanks for your attention.